Thank you all for having me, and also like to thank my collaborators in Brazil, and also Hector Zenil, whose financial support made my travel from Brazil to the UK financially possible. So I'm presenting binarized neural networks converged toward algorithmic simplicity, empirical support for the learning as compression hypothesis. So the main issue we are addressing here is that many times neural networks are viewed as only doing statistical pattern matching. And because of this statistical framing, the most usual way to compute or measure actually the complexity of a neural network is using entropy-based measures. And of course, we agree with this statement that neural networks are doing some kind of statistical pattern matching, but what we would like to understand also is if neural networks are also doing some kind of structural pattern matching. In other words, are neural networks merely memorizing the general features of the data, or are they also capturing some kind of deeper algorithmic irregularities within the data? So we propose using BDM, which is the block decomposition method, which is an approximation of Kolmogorov complexity to assess the complexity of neural networks. And we are doing a small experiment. So it's a very simple one. We are using binarized neural networks, actually small binarized neural networks, and we are assessing if the training loss correlates better with BDM or with channel entropy. And of course, if BDM has an advantage, that would mean that neural networks are also doing some kind of structural compression, algorithmic compression actually, and transforming random weights into structured configurations that encode task relevant information from the data set. So one of our main motivations for this study is because we have a lot of different techniques to enhance neural networks that are based in entropy-based measures. So adjusting the model size dynamically, using the entropy stabilization as a stopping criterion during training, regularizing loss functions. I think this is like the most common used one, and also post-training compression. And most of those methods are based in the minimum description length principle, which I think many of you have like presented yesterday, and which states that the best model is not only the one that has the best predictive encoding of the data, but also the one which has the minimum description length of the model itself. However, the MDL principle proposed by Rissanen was actually inspired originally by algorithmic complexity. So what happens now that we have like better measures to approximate Kolmogorov complexity? Could we use them instead of these metrics, instead of using entropy-based measures? And other motivation that we have is that we have some claims from the field of neural networks, machine learning. I have here some quotes from Ilya Saktivir, who says in his talk in the Simons Institute that maybe neural networks are doing some kind of program search during training and acting like, he says, mini Kolmogorov compressors, in the sense that neural networks are implicitly searching for the short search program that explains the data. And if so, the implications are quite interesting because neural networks may be going beyond statistical pattern matching. They could be also be internalizing the causal and generative structure present in the data. And this supports new learning frameworks based on IIT. So we can use like AIT measures to do the optimizations and enhancements to neural networks that was done before by entropy-based measures. So the central question of this presentation is, should neural network training be also understood as algorithmic compression rather than just statistical fitting? And this is very important that the claims that I'm going to do and the findings, the experiment are constrained by binarized neural networks. So I'm not generalizing saying that this works for transformers, sparse neural networks, or other types of networks. So a little bit of background on the methods that I use in my experiments. So first, we are going to use BDM, as I said before, and BDM use CTM, which is a method for calculating the complexity of the Kolmogorov complexity. Actually, is approximation of Kolmogorov complexity using small Turing machines based on algorithmic probability. So if you would like to calculate the complexity of, for example, 4x4 binary matrices, what we're going to do is enumerating all the Turing machines up to a certain size. And we are going to run all of them until they're hot using the Busy Beaver values and record their outputs. Sorry. Having something?
just fine. Run the Busy Beaver.
Oh, sorry. Yeah, no, using the Busy Beaver is too hot, but there are also other types of optimizations here. No, sorry. But no, but are quite limited. Yeah, but we are not. We don't have like the Busy Beaver values, but we use some optimizations using also the Busy Beaver values. But yeah, we're not using them because we don't have them. So until I think BB6, we don't have them actually. So yeah. And we're going to record our outputs, and we are going to see all those patterns that these halting Turing machines are generating. And because of this, we are going to have an empirical approximation of algorithmic probability. So for a certain pattern X, I'm going to see all the Turing machines, calculate the number of Turing machines that halted upon this output X, and divide by the total number of the halting Turing machines. And then we can use the coding theorem method by Levin to estimate what is going to be the Kolmogorov complexity using the estimated algorithm probability here. And of course, we don't do this in running during running our experiments. We have like computed all those values for different classes of strings, 1D strings with 2 to 9 symbols, with max length of 12, and also here 4x4 binary matrices. And we did this pre-computed, and this results us in a lookup table that we have here, an example. As you can see here, we have this pattern that looks a little bit more randomish, I would say, in comparison to this one that looks a bit more structured, and this one has like a higher complexity here estimate. And yeah, this is the CTM method, and it is, of course, because of this, it is so computationally costly. We only do this like for small objects because it's very expensive. So how do we compute the complexity of larger objects? So let's suppose I'm going to explain BDM, which is an approximation of algorithmic complexity for larger objects. I'm going to present it illustrating this example here. So we are going to decompose this bigger object here in the objects with the CTM dimensions, so 4x4 here. And we're going to find each one of the unique patterns and compute their CTM values and add here a log penalization for the multiplicity or the number of times that this object appears in this bigger object here. And then we are going to sum those complexities and also this multiplicity factor here. And because of this formula, I think you can see that what BDM does is combining local algorithmic complexity via CTM with entropy-like penalties at larger scales. And that's what happens when the object is too big, is that it converges toward channel entropy. So, and this is also being validated. We also identified some strings which have maximum entropy, but low BDM and CTM values. And of course, something that you could ask is like, which kind of reference of Turing machine that you're using for calculating this algorithm probability? But we have like tested different types of computational models, and they converge pretty quickly to the most probable, algorithmically probable patterns. And the object of our study are binarized neural networks. And I'm going just to do a quick recap on binarized neural networks. So they're very, very similar to normal standard neural networks, but they have like two key differences. First one, we are going to binarize the activations and the weights of the neural networks. So positive values will be +1 and negative values will be converted to -1. And of course, this makes it like discrete. So how you're going to allow the gradients to flow. Use the trace estimator for this. Basically, we're going to treat this sign function as an identity function, and we are just ignoring the gradient of the sign function. And this allows us to perform stochastic gradient descent as usual. And yeah, it's important to remark that although the name is binarized neural networks, the gradient passes through real value weights, and the neural network has real value weights. So here we can see the diagram. The only differences are that we are binarizing the weights and activations, and we are going to use the straight estimator to allow gradient descent. So how do we calculate now the complexity? Oh, sorry.
Run it, it's binary?
When we are doing inference, it is binary. But when we are doing backpropagation, it is, so we calculate the error, the loss, using the binarized weights during inference, but in backpropagation, we are using the real value weights. So how do we measure the complexity of the binarized neural networks? It's pretty straightforward from what I explain later. So we are going to binarize the weights here. So first we binarize them, and then we do a block decomposition following BDM as I shown before. And we are going to find all these unique blocks across all the weight matrices that this neural network has. And we are going to compute the complexity using BDM. And for the comparison that we are going to do is BDM against channel entropy. And we are going to use those same blocks to compute the channel entropy of the binarized neural network. First.
The zeros and ones of blocks.
The patterns of the blocks.
So B is what?
Is the pattern of the block here. So
you're going to break it up into these 6 blocks, and you're going to work out the probability of each block.
Yeah, exactly. So for the experiments, just making a quick recap. So we are going to evaluate which one better tracks learning dynamics, BDM, or channel entropy. And the hypothesis is that if BDM better tracks this training, it will have a bigger correlation. And the rationale here is that the advantage that BDM would have over channel entropy will be because of the algorithmic structures captured by CTM. So the experimental setup here is very simple. We are using MNIST dataset. The dataset, I think all of you know, like handwritten digits classification from 0 to 9. But we are resizing the digits from 28 by 28, I think, to 10 by 10, because we would like this regime where we have small binarized neural networks and not like huge ones, because in this regime, BDM would converge towards channel entropy. So yes, this is a very limited study. And then we are going to stratify sample 200 data sets. We're going to sample half of the data set 200 times for doing later bootstrap sampling. And we are going to use a simple model architecture here, a binarized multi-layer perceptron with 2 hidden layers. And these are the layer configurations that we have here with number of nodes in the first hidden layer, in the second hidden layer. So they are pretty small, as you can see. And the training procedure is very simple. We are going to train each one of these current configurations 200 times, but we are using early stopping. And this is important because we would like the regime where we are seeing the generalization process. And we would not like to see the regime where we have like some kind of memorization, because then we would know that the network is actually trying to memorize specific regularities from the data, and the entropy and the BDM would increase. I also did some study that I'm not presenting here about what happens in this regime. I can talk to you during lunch. And well, during this experiment, we are going to compute BDM and entropy values for each model update, so in each backpropagation step, and average them per epoch. And for the evaluation, we are going to normalize here using very simple log transform, Gaussian smoothing, min-max scaling. And then we are going to use Pearson correlation for assessing linear relationships and Spearman correlation for assessing monotonic relationships. And then we are going to generate bootstrap confidence intervals with 95% confidence intervals. So the results are pretty interesting. R here stands for Pearson correlation and Rho for Pearson correlation. As you can see, both metrics have high correlation, indeed, with the training loss, and BDM always have an advantage over entropy. And which that means is that actually, yeah, algorithmic complexity measured by BDM in this case is actually having is actually better tracking the learning dynamics from these binarized neural networks. And as you can see, as the network grows, as the network grows, this advantage that BDM has over entropy diminishes. And I have some explanations for this, but I'll explain in the next slide. And of course, we tested the accuracy of the neural networks because we want to see that they're also learning something. So they are learning above 10%, which is like the random guess. So Yeah, they're actually non-trivial learners. And yeah, then we can assume that BDM better tracks algorithmic complexity is having an advantage because of CTM in comparison to channel entropy. And here are the different plots for the different architectures with different sizes. And here, as you can see, as I said later, BDM, the bigger the model, more BDM behaves like entropy. And this happens because, as I said before, because of the log penalization in the BZM formula, because when you have like a big object, this log penalization is going to dominate over the CTM values that we had. And so we also did something that you might ask is, sorry.
So the BDM complexity starts maximum.
Sorry?
The complexity starts high and goes.
Yeah, it starts high. Yeah, because of the randomness initialization. So starts high and then goes decreasing, and after overfitting starts to go higher. Is that it? Okay. So you might ask, you might assume when I like make these criticisms that maybe what we are assessing is not that the neural network are actually encoding the information from the data set, but the neural network is actually, you are only like tracking the dynamics of learning neural networks. So for assessing this, we did random data control experiment. Was pretty simple. We used like the same setting as we did it before, but we use we use like noise. We sample from uniform mean distribution here to generate noise and train the neural network with this noise. And we trained with fixed with 15 epochs, as we don't have validation loss in this case. And we saw before that we would have, for this type of architecture, an advantage of BDM over channel entropy. But in this case, the results were quite different. Now we have entropy a little bit better in comparison to BDM. And actually, it's not better. It's actually the same because they are like, they are within the confidence intervals of each one. But this proves that when BDM loses this advantage that has over entropy when in the regime when we don't have like structured data.
I think just one thing you should maybe as a small addition, comparing to entropy the way you calculated it is maybe fine, but it's a slightly strange null model. I feel like if you were to show somebody this array of squares and stuff and say, pick some off-the-shelf compressor, they probably wouldn't break it up into parts and use the channel entropy. They probably then derive it or C2W it or just, they just compress it, turn it into a string and compress it. So I feel like comparing your comparison of the way you've chosen to estimate it by entropy is a little bit odd. In which case it means a slightly strange comparison that I find which was a comment. I mean, it
makes sense.
Just to use one or two other measures beyond just entropy.
Yeah, I think we also could do like some different kind of partitions of the weight matrix, but your
yeah, and then just the way it's presented is here is VDM and it's working better than entropy, but I don't know that many people. Maybe, for example, if you showed me that pattern and say estimating complexity, I wouldn't have estimated it by entropy in that way in the first place. So to say that it's better than that one is kind of
understood it. Yeah, we did this because we would like to get like the statistical to have like a fair comparison between channel entropy and BDM by by doing this like shared block decomposition. But you are right. If I would like try to calculate channel entropy specifically for a neural network outside of this scope, I wouldn't use this kind of partitioning. But since we were trying to find if BDM has a little bit of advantage because of CTM, we did this for having this kind of comparison. But I agree with you.
I mean, that's exactly the point there. If you're trying to show that it works better than something, it would be logical to use what would be standard comparisons rather than a particular choice of comparison, which anyway, just a comment there.
No, but I totally agree with you. So the conclusion is that we could support our findings support the view that training is not just statistical pattern matching, but also has some kind of algorithmic structure within the data, within the weights of the neural network. And they're doing more than mere memorization. So here's a quick recap. So if the dataset has structure, the correlation between BDM and training loss will be higher in comparison to entropies. If the data is random, they're going to be actually the same. Some issues that we have for analyzing other types of neural networks, so for example, larger scale and more practical ones, is that BDM, of course, as I said before, will converge towards channel entropy. So we would use like some channel entropy measure because BDM will lose this sensitivity to algorithmic structures. And of course, we could also do this, and it would be pretty straightforward to use BDM for real value weights. But the issue is that when we are doing this conversion from real value to binary values, we are going to also need more bits to represent real values, and then we are going to fall again in the scalability issue. And the last part is that I would like to use BDM for using as a regularizer, like MDL style training, but the problem is that BDM is not differentiable. I have worked on this, so I could do like a differentiable version of BDM, which I call soft BDM, but it didn't work as a regularizer. But if I put it just this differential version in the loss as the only term in the loss function, I could actually use backpropagation to reduce the complexity of the neural networks. But I can explain later if you want during lunch why this does not work as a regularizer. So yeah, that's it. Thank you.